So, hello and welcome to the Best Is Yet to Come talk, in which we'll look at the state of Akka in 2017. It's going to be a bit of like where it's coming from and the reasons for some of the modules, and a look forward at the both current, fresh modules and what we're looking at in the future. Having that said, it's not a really official like outline or roadmap. However, it's really what we're kind of thinking of going forward towards. So, for those who don't know me, my name is Konrad Malawski. I work at Lightband on the Akka team, and I'm part of a team here at GeeCON. So yeah, I've smuggled myself a bit into this conference, but I do hope you'll enjoy it. And yeah, some other things I've been doing here in Krakow, including the software craftsmanship group or the Polish JOC. So, anyone who's not heard of Akka, actually? Not heard of Akka, okay, 2 people. So there's gonna be a super brief summary for you. But in general, we're gonna be going through all of the things Akka provides. So probably you'll have a good idea what it is and can get started afterwards. So in general, the entire principle of the team and the project itself is, can we do better than that? So we look at some existing, state-of-the-art technology. We think, can we do better than that? And we try to do so. And a mini personal motto that I've kind of started thinking recently a lot is, when other people or other projects start doing some reactive programming or reactive systems and start looking at the manifesto, yeah, you know, we've been there, we've done that, and certain things don't work. And I'm happy to talk about what doesn't work and what does in distributed systems. We'll talk a bit about that. So, reactive, and if you're curious about the term and what it actually means, I wrote a mini book about it for O'Reilly. It's completely free, you can get it online, just Google for why reactive. However, the super short version is there's these 4 tenets, and really the goal is to have responsive applications which react both to failure and to load, so they need to scale up and down. That's the elasticity part of it. The resiliency is obviously in face of failure. And how do we achieve this? We use message-driven APIs. In contrast to, for example, remote procedure calls, which are not that native to distributed systems. It's more like a tag-on, and we'll see why I think so. So with message-driven as the foundation at the core of Akka and the manifesto itself, let's see what it actually means. So probably you've seen or heard the term reactive programming, and it's a bit confusing, I think, actually, because the term reactive programming has recently become very mainstream, but it also is just a small part of the pie. So you can build a reactive application with reactive programming, so like RxJava, Akka Streams, that's also one of those things, or some other competing libraries. But that's not everything, because you want to build a reactive system. So if your system is only a single node, okay, that's cool. But most of the time, you never really have an application that's a single node. It's always multiple nodes. It's always multiple applications talking to one another. So we really talk about systems, and the system should be resilient and scalable and fast, not the single application. That's not helping anyone if only a single application is fast, but everything is down anyway, right? The user is not really benefiting from a fast but offline application. So, and while we talk about this, let's keep in mind, that's a mini picture from the book I just mentioned, that there's kind of 2 realms to it. One realm is on the inside, which is where we have full control over both protocol and technology. Usually this would mean that a single team has control over this. So it could be a single microservice, and we're inside the microservice. And then there's the outside. And the outside and inside have very different requirements. So some people would advertise doing the same technology both on the inside and outside. It has upsides, because then it's okay, we do JSON and HTTP everywhere. However, it also has downsides, because the inherent nature of HTTP is not very good for certain kinds of applications, which are, for example, streaming or peer-to-peer or highly dynamic in nature. So peer-to-peer again. So, for example, the typical trade-off that we advertise here is we can do way faster or more efficient stuff internally, like binary encodings, binary protocols, and just way more resilient designs than just slap everything behind a load balancer. Then on the outside, where everyone basically demands from us to do some HTTP API, probably with JSON and probably with XML if we're a boring company, right? So there's different trade-offs. So, for those who raised their hands that they have no idea what Akka is a toolkit. Let me underline that. It's a toolkit, it's not a framework. So we try to provide these building blocks or tools that you can pick and choose, and then you build your system out of them. If you don't want a hammer, you don't need to use the hammer, right? It's over there. It's not inflicting any both dependencies or complexity on the other parts. So, for example, if you don't want clustering, you don't use clustering, you don't have clustering. It's by definition trying to be very separate parts, but they should integrate well. In contrast to a framework, so for example, what's a framework? Play framework would be a framework. Lagom, Spring is also kind of on the edge. I would claim it's a framework because it's so infestive to a code base, and then you have it everywhere and it's hard to get rid of it. And yeah, so that's the main difference. And yeah, we're message driven at the core. You'll see what that means. A quick list of the modules we have. You don't need to look into them because basically this talk is about explaining how and why we got to having all of these modules and what they actually contribute. And as a reminder, because sometimes people forget that we have full 100% coverage of both a native feeling Java API with all of the new Lambda stuff, etc., and a full Scala API. So yes, it's a it's a library implemented in Scala. However, everything has a full and Java feeling API. And we spend a lot of time on it. It's not like I just claim we have a Java API. We spend a lot of time on it so that it feels good even if you don't want to look at Scala at all. That's fine. Although you'll see it's way more concise. So I'll leave the choice up to you. So this talk is structured like a journey. So a bit of the past, and we'll see what we were working on and what we're up to in the future. So let's start with the beginning of Akka, just in general. And that's actually 2009, which was also the first GeeCON conference. So funny side story. So Akka back then was founded by Jonas Bonnier. Around July was the first release, 05. And basically Jonas, previously he did Aspect J, and he was consulting, he was building distributed systems, and he noticed, yeah, wouldn't it be nice if I could use all of the Erlang failure handling semantics, right? So Erlang has this let it crash philosophy, and that's what we adopted. So the failure handling in Akka, in actors, is very much inspired by Erlang. It's slightly different. I can point that out if you're interested. How specifically? But he didn't really want to switch to the Beam VM. He wanted to stay on the JVM, and at the same time he discovered, oh, Scala, pretty nice language, let's try that. So this is how Akka was born. And the first and core and still the most important thing in Akka is Akka Actors, which implement the actor model. So the actor model is those three rules. So maybe let me first ask, who knows what an actor is? That's cool, look, most people know, so I can skim over it. So that's an important thing to remember. An actor can only do three things: send messages, receive messages, and create more child actors. That's the only thing it can do. Even if you do like timers or anything else, that's gonna be modeled as receiving a message. So that's maybe the most important thing you can learn about actors from this talk, because people always talk about them, oh yeah, it's better than threads. Yeah, it's certainly better than threads. It's way easier to build concurrent applications with actors than it is with manual volatile management or logs for that matter. However, it's not the most awesome part about it. The most awesome part about actors is that it's a distribution construct. So by distribution, we use the term location transparency for it as well. It means because of the way an actor works, it doesn't matter if it's a local interaction or if it's talking to an actor on a different node in the cluster, or if that actor has suddenly been moved to a different node. You don't even need to care at all. So compare that to RPC, right? If people build systems with, I don't know, gRPC, any kind of RPC system, then it goes the other way. So it tries to make the remote calls look as if they were local calls, right? So what we do in Akka is we make, by default, even the local interactions look as if they were remote interactions. So everything is a message sent. So the difference is that on the network, it makes more sense to talk about messages because we talk about packets, we talk about message loss, we talk about redeliveries. So it makes more sense to go in that way. There's less impedance mismatch. So I figured I'll not do the typical hello world actor, but at least something that you might see in a real world, which is that. So I grayed out a bit of boilerplate. So this is the messages that it can handle, right? It's in Scala, so you can just say case class and that's the fields. And then you extend an actor. Here you have some lifecycle management, very important part of actors, that they have lifecycle hooks. So when an actor starts, gets restarted, fails, you get these callbacks. And you can handle your failure more explicitly than just wrapping everything in try catches, etc. And then the core of the actor is really the receive method. You get this message, you can reply to the sender of that message. Simple, right? So that was in Scala. I do want to show the relatively new, I think it's a year old or so. Well, actually no, like half a year maybe. Because we changed the Java APIs to feel a bit more Java 8-ish. So nowadays you can emulate a bit of a pattern matching that you saw in Scala and Java. So you can say receive builder, match on this class, then run this code block. It's not as concise, but it's close enough. And in none of the Java APIs is there Scala API leaking. So you have a nice, well-defined API for whatever language you're using. So supervision works. That's the difference from Erlang. So in Erlang, you have to explicitly link to have failure handling. So one actor or process can watch another and then get failure notifications. In Akka, there's always the parent that will be automatically watching whoever child actor it started. So it's a simple parent-child relationship. And as you can see, you can have multiple children, of course. So, simple actor interaction. We talked about that. And you can reply to whoever was introduced to you, right? So that's the peer-to-peer nature, right? If someone tells something to Bob, it's an actor ref, I tell directly to Bob. I don't go, there's no reply, right? It's not request reply. It's message and message. Okay. So, and we favor binary over textual protocols. A great quote about that is that the internet is running in debug mode. A friend of mine said that. It is. I mean, there's a lot of text being thrown over the wire, and it's very wasteful. I mean, in so many applications, I've been trying to help a customer do some performance work. Like half of the time would be spent parsing XML or JSON. It's just such a waste of computing power to keep parsing the same data all the time. Binary formats can be a bit more efficient than that. Example, imagine some data structure like that. We can represent it in a protobuf, which is what Akka uses internally, and you can use that as well. Then it waits around 200 something bytes, right? That message that I just showed before. With Thrift or Jackson, with manually preparing the marshaller, yeah, you have a 2x already, so it's a bit heavier. But the real problem is really that half of the world is still using Java built-in serialization. and you can see both the size and the time difference it takes for serializing and deserializing these things. So for one thing, don't use Java serialization for performance reasons. For another thing, don't use it because security. There's a hell lot of attacks on Java serialization, and there's always coming more. So just don't use it. Another visualization of the problem. So here's this case class serialized by Java serialization. You can see it also contains all the names here because it is very explicit in what it sends over the wire. So even in XML, this case class is smaller than the Java binary representation. So when I say use binary, I don't mean use crappy binary. I mean like use a good binary library. Because in Cryo, it would be more or less like that. So you see it still keeps the names around in the type. So how not to touch Java serialization at all? We have a flag for that. Another new thing which you may not have seen, and I highly recommend to just switch that on, or off, should I say. So just disallow Java serialization. And it's really good for security and then performance. And then you'll have to somehow do serialization for your case classes, right? Because you disabled the Java one, which automatically works. You need to do a bit of extra work. The extra work isn't really that much, because libraries like Cryo. There's this community project by Romix, which you just say, hey, here's my serializer using Cryo. And then you just say, okay, which classes should be serialized using Cryo. You can't just list all of your classes there. The reason we do want to register the serializers explicitly like that is again for security. So no one suddenly loads a class and you start sending a malicious class around, right? So if you well define your list of classes that you can serialize, it's a bit better for that. Random side note. So at some point, Akka had futures, as in the library was implementing futures. And now you may ask, hey, yeah, but Java has futures since forever. Yeah, but the Java one wasn't very useful because it forced you to block to get the result back, right? You know that, right? So Scala didn't have futures back then in 2012. However, the need of a future-like concept in a reactive world is so great that basically everybody was implementing futures, including Akka, Finagle, Scala Z, who else implemented futures? The Lift people, and I think a few more implementations. So the fun fact is that the Scala futures originated as a collaboration of these three, and basically, if you look at the team who was working on those, like half of Scala Futures team is basically the Akka team. Like, random fact. So, and we'll get back to that, because this is actually, it's kind of important to the story we're building out here. It's not that much about bragging, hey, we did futures, because it was, as I said, many people did them very nicely, especially the Finagle's ones are very good, and still have features that the Scala ones doesn't. But, okay, so we have futures. We're around 2012 or so, and we have circuit breakers. So circuit breakers not a new thing, but at the same time, are they, because people say it's a best practice to put circuit breakers around asynchronous code or blocking code that can fail. But is it really the solution or a solution of a like old thing that we probably could solve in a different way? So imagine a service, you're overloading the service with too many requests, and then it starts breaking. So what you do is you open the circuit breaker, you give it some time to breathe, and then you resume operations as usual. So circuit breaker opens, and then you send one request again. If it's okay, then it's okay. If not, then you keep slamming the brakes. But this mode of operation is a bit like you have a car, you drive it into the pole, you have a car again, you drive it into the pole again, you have a car again, etc., etc. So it's not very graceful. So remember this, as we'll go back to this. As circuit breakers are absolutely useful, but for failure handling, they are not as useful for flow control. Because, I mean, they just don't do that. They do slamming the brakes. They don't do gradual control over how fast we should send the data. And we're always guessing, like, can I send the element? Can I not send the element? So this is what we certainly can do better. And this is what Akka Streams and Reactive Streams is basically. It originated from this, okay, we have a lot of futures, okay, we slam circuit breakers on them, and then the realization of, yeah, we kind of need to do something better than that. Before we do that, let's talk about the distributed side of Akka. So it's really at the heart of distributed systems in Akka. It provides failure tolerance, and if we were talking about, okay, if an actor can be on a different node, that's basically what the cluster provides. The killer feature there is sharding, so you can send a message with a given key to the sharding subsystem, and it will figure out where to route the message, okay? So the person responsible for the fifth, like, K5 request message is on that node. And if a node fails, and we know there was some actors on that node, then the actors will be started up again with the same name, same identity, on a different node. So it's failure handling and rebalancing. We'll get back to that again in a different module. So we talked about inside, outside. So far everything was inside of your application or system or your microservice. But by the end of the day, we need to talk to the external world. Nowadays, that basically means some form of HTTP. So Akka HTTP, which I nowadays maintain with Johannes Rudolf, originated as Spray. You may have heard about the Spray library, excellent piece of code. However, when we decided to pull it into Akka itself, we decided to do a full rewrite with the goal of making it a streaming first HTTP server. Because Spray was based on actors, which is good for concurrency. However, it wasn't dealing well with, for example, long-running file uploads or streaming APIs. Let's say you have some sensor and you want to keep streaming the data points from the sensor. So it wasn't that good in those kinds of APIs. So what we did is we took Spray's full HTTP model. So every single piece of the HTTP spec and more has a representation as a type. So you cannot possibly put wrong stuff in wrong places. And it's a streaming first server, which is pretty interesting for those streaming applications. And it got a Java API. So as I said, we take the Java API thing very seriously. And now here's a chicken and egg problem, because the here is Akka Streams, which we didn't show yet. But imagine that. So an HTTP server, for example, Finagle, represents an HTTP server as a function from an HTTP request to an HTTP response. Very nice way to think about it. We took that a bit differently, and we model it as a flow. So a flow is an Akka Streams abstraction, and what it is, it's for any number of input elements, so it can get one request, for example, it can emit any number of responses. Yeah, why would I do that? Turns out this is exactly how we can model server-side push in HTTP 2, right? So we didn't, at that point, implement HTTP 2 yet. However, we were looking at, okay, this API needs to grow, we need to make it future-proof. An HTTP entity, however, is basically from the TCP layer, can pull data. And again, it's an Akka stream. WebSocket is exactly the same as an HTTP server, basically. However, it talks about messages, because the WebSocket spec talks about messages and not bytes or requests. Okay. Has anyone who has not seen Spray or Akka HTTP? A few people. Okay. So this is an entire server, an entire application. The few things to note, so the actor system, that's basically where all of the actors run. The actor materializer is what makes the Akka Streams run, because we have a materialization step there. And then basically here's your routing DSL. So any request that starts, that goes to the path hello, and it's a GET request, complete it with this, please. And we have some more nicer ways to express that. So you could just say complete and give it just a string, then the content type would be inferred automatically. So things like that. And I said we have, oh, I didn't say, but we have two levels of the API. We have a high-level API, so here you have this nice DSL. The Java one looks pretty much the same as this. it's just more semicolons. And we have a low-level API in which you can see, okay, the HTTP request, it's a GET request to this path, and here's things like the HTTP entity, the headers, etc., etc. So you can match on them. Okay, so we have inside world, outside world. What can we do more? What's the next thing you need in your application? At some point you need to persist stuff, right? Because if you're just running in memory, you're probably not going to be very, for one thing, resilient, and for a second thing, you're probably not doing very important stuff if you don't need to store things, right? So Akka Persistence, again, came out of an initially open source library developed by Martin Krasser that used to be called event source. And similarly as with Akka HTTP, we decided to collaborate and improve it a bit, kind of make it a bit more polished, let's put it this way, and release it as Akka Persistence. So Akka Persistence, I think that's the first thing I really worked on when I joined the team and company. And it basically allows you to implement event sourcing. So the name is persistence, but it's not like any kind of random persistence. It's specifically about event sourcing. So you receive commands, you store events, and if you want to, you can do a query that's populating the read side of a CQRS architecture. So why do we want that? So actually, the reason for us wasn't as much to do CQRS. It was to have a nice and fitting way to have the actors migrate between multiple nodes, right? We talked about cluster sharding. Okay, a node dies, we kill the actor, we put it to a different place, but the state was lost. So what Akka Persistence fits perfectly to is because actors operate on messages, it's very easy to, and very right feeling in a way, to persist these pieces of information, and then you replay the history contributing to the entire state of the actor. So this is why we picked event sourcing, because it fits to actors and not just serialize the entire actor and put it in a database. That would feel wrong, right? And as a side effect, it's a perfect tool for CQRS. One thing to note, so we do all this, okay, the actor has died, we migrate it, we replay the events, but we also, because it can keep receiving some commands from the outside world, right? So what we do is, because the actor is not ready to process these messages yet until it has processed all of the past events. Imagine like the events are, you got $5, you spent $10, so you have like -5 in your wallet. So if someone were to ask you, give me money, you probably shouldn't do that because you're on minus account balance anyway, right? So you need to replay the events first. So we do the buffering for you. It's completely transparent. The API differs a bit, but not much. The reason we decided to make it differ is to make the replay explicit. So when you're replaying, the messages will be delivered to the receive recover method. And here, okay, event, and if it's a snapshot, I update my state. And if it's just an event, I update my state and can receive the new one, right? So here it's mutate the state, and here it's assign the entire state that was serialized. You can do snapshotting. And then commands are put in here, so it's receive command, and you can persist events as an output of that. So, finally present and future for the second part of the talk, which is around 2016-17, because the other years, including Akka Streams actually was kind of in the previous era. So, distributed data, that's a new thing. So, anyone not heard of the CAP theorem? Hands up. Okay, so quick explanation. CAP theorem is about, there's this a few free capabilities in distributed systems, which is, okay, you can be consistent, you can be more available, or partition tolerant, and the CAP theorem is that when it came out as a talk and later a paper, it claimed, okay, you can only pick 2 of them, which is actually false. Yeah, you can pick 2 of them, but you can't ever sacrifice partition tolerance, because if you sacrifice partition tolerance, you basically build a useless system. It completely useless if you're not partition tolerant, because the entire goal of these trade-offs is to tolerate the partitions in one way or the other. So what do I mean by that? Akka persistence picks the consistency side. So there is always one actor, it is their identity, it is their place where decisions are made. And this way we can scale it very easily because, okay, it's a single point, but for every small piece, so for every actor, it's a single point of coordination. It's not a global lock. It's a lot of single pieces that make decisions locally. So, but sometimes that's a too strong requirement. Sometimes you want availability. So the availability example is the Amazon shopping cart. Maybe you've heard that example. It's about, okay, my cluster is having some trouble, but I have customers adding and removing things from the shopping cart. I don't want to be, I'd rather be available to them to put stuff into the shopping cart than tell them, yeah, sorry, we can't store your information right now. We can't store your entry of an item to the shopping cart. You don't want to do that. You want to insert the thing. And eventually, if they click, yes, I want to buy, and you noticed there was some conflicting rights or reads, then you can notice, oh, we're not quite sure if you inserted this computer or not. Could you please make sure, do you want it or not, or something like that. Right? So that's the available side. So the difference is really that we don't talk about the entity, we talk about the data and how it disseminates in the cluster. So the difference here is really that we use an extension, so okay, distributed data from the actor system, and the replicator is what is responsible of disseminating the data in the cluster. It's using a gossip protocol, and it randomly picks a few nodes and will chatter to them your updates. So if you do an update of a counter, for example, here's a counter, where's the counter? Here's the counter. We can write to the counter, and if this has completed, we get an update success or an update timeout. Also, if a different node makes updates to this counter, we would get updates to the data structure. So, the interesting thing here is that you can pick how consistent you want to be. So if you want to be available, you're using this distributed data thing. However, you use the write all requirement. That basically means your write will not return until all of the nodes have seen the write. So you're more consistent in a sense. You can be less consistent if you pick, okay, just write local or just write to a majority of the nodes. But that allows you to return quicker and confirm to the customer that, okay, we got your write, we got your insertion of a thing to the shopping cart. So you have a lot of control over how to write things. So, Akka Streams, as I said, came from the realization that we somehow need to control this flow control, and also from a collaboration with Play and RxJava back then, in which we realized we need some kind of streaming abstraction, and all of us were implementing their own thing. Let me just skip ahead a few. Yeah, Reactive Streams. So everybody was doing a bit of their own thing. So Play had iteratees. It solved the problem. It was a bit difficult to use the API. It was very Haskell inspired. Akka had some very low-level APIs for I/O, so writing TCP and UDP. We had backpressure there, but it was difficult to handle for users. You would have negative acknowledgements, and you would have to retry writes again. And then Ben Christiansen, back then at Netflix, was working on RxJava, supporting the reactive extensions from .NET to Java. And his need was more about, okay, I need to do some asynchronous programming. And back then, he didn't yet need all of the backpressure things. He did realize a bit later on. So basically, we all were working on the same kind of thing, but from different aspects. So Reactive Streams is basically a collaboration of those main forces, and then we also invited people from Spring and Red Hat to join and design this thing together. So this is actually included in JDK 9, it's already merged. And once JDK 9 is finally out, we'll be using the Java util concurrent flow interface, which Akka Streams is an implementation of, right? So, but what does it do? So it solves this case when you have a fast publisher and a slow subscriber. If you think about the killing the downstream, that's pretty similar if it would be about overflowing buffers. It's not about completely failing, it's about controlling the rate at which we write data to such that it's not faster as the downstream can process it. So the question is, what do we do if there's an immediate buffer overflow? Sometimes we say, okay, just drop the messages and require them to be resent if you really need to. People sometimes freak out when we say that, but sometimes that's a completely valid answer. And it happens all the time on the lower protocols, like TCP does this all the time. But can we do better on application level for that? So in one slide, Reactive Streams is basically a permit system. If you know your buffer space, so a number of elements, and you process them asynchronously here, you know, okay, I have 3 slots available in my buffer, so I will advertise that I can receive this and this many elements. And the upstream can only send 3 elements until it gets more permits again. So as I said, that's coming to the JDK, and I need to speed up a bit, sadly. So, and it's not an end-user API, it's more of an SPI. So you're not meant to implement them directly all the time, because, well, the API is pretty simple, like 7 methods, but all of the concurrency rules that you need to adhere to, that's this wall of text, and some of them are pretty tricky about memory visibility of writes and things like that. So you should know that, okay, I want to be using Reactive Streams that gives me this flow-controlled manner of sending data. However, you'd be using an implementation thereof, for example, Akka Streams. API, very similar to either RxJava or Scala collections. You have map, filter, and all kinds of operations, but they do work on streams, not on collections. Okay, so that's API summed up in code blocks like that. So a flow is something with one output, one input. Now we know, okay, that's the HTTP server. A source could be the TCP connection, the entity side of it, etc. So, looping back to HTTP again, we build a second port because, yeah, we want to do HTTP 2. Why do we want to do HTTP 2? For one thing, it's about time, but that's not a really good answer, right? So, let's look at an API that's just serving images. That's more interesting for web pages, not as much for APIs, but APIs benefit a lot from HTTP 2 as well. So this is how loading such a page with really big images would look like. There's a lot of stalling. So gray is the connection being stalled, and there's 4 or so connections open here, and it completes in around 5-6 seconds, right? On the same computer, on the same setup. Oh yeah, and each of the connections needs a full SSL handshake, which also takes some time. So the same request response cycle on an HTTP 2 connection. 2 differences here. One is there's only one connection, and we actually pipe all of the data through this one connection on substreams, and all of them can be sent at the same time if we want to. It's up to the server to control how concurrently or how prioritized it sends the data. But even with a trivial implementation that doesn't do any prioritization, we already basically halved the response time of this page. And this is already working in Akka HTTP. We're working on some missing features and tidbits there. So, one interesting thing, I think we'll get to it in the next slide. So Play will be switching to Akka HTTP as the default backend. One of the reasons is exactly that we did Akka HTTP 2 support. Now the mini subjourney about Akka Typed. I know many people are very excited about it. And maybe a bit of, again, explanation why it took so long. One is, I mean, Akka is obviously very inspired by Erlang and distributed systems in general. Types do not really fit that word that much because of a concurrent and distributed nature. However, let's see how we got to the current APIs. So back when Jonas and Victor were working on it, the idea of typed actor was mostly to show something to Java developers that they wouldn't be too afraid of. So yeah, it basically would declare a API like that. Oh yeah, it's a future that would be transformed with code generation into messaging. But, you know, for example, this one here, the square now, this would be a blocking call. We don't want blocking calls. The entire purpose of using Akka is not doing any blocking. So we don't think this is a good idea. And it served its purpose. So don't use it. Now, the second attempt was Roland from the team hacking on typed channels. The typed channels looked like that. You don't need to read very into it. But you can see the type signatures are going very complex very quickly. And sadly, we decided it's too much overhead and also too much funny operators. We actually don't do much funny operators in Akka. The three operators we have in the entirety of Akka is the question mark, which is the ask, the tell, which is the exclamation mark, so actor, tell, message. And the third one is in Akka Streams, if you want to connect two flows in a really advanced API, then it's a arrow operator. So we decided, okay, this is adding too much complexity. It also needed Scala macros and other complicated stuff, so we dropped that. Many years passed, and we kept thinking about it. And then the reactors pattern came out. A bit ill-named, but very good paper by Alexandra Prokopec and Martin Oderski, which inspired us to have a second look at it with a different perspective, and we arrived at a process DSL and the Akka Typed API. So we provide two styles in the new API, and it's currently in snapshot mode, so we want your feedback about it. And so it's actor mutable and actor immutable. So by mutable we mean there is an easy way to have some mutable state and mutate it, in that sense. And the immutable API, which I'll show in a second, it's a more functional style. So the differences from normal untyped actors are actorf finally has a type, so we can only send messages of type T or subclasses of that to that actor. Instead of actors, we implement the behaviors, kind of keyword spoiled already, in behaviors. So the thing you implement is behaviors, and the behaviors can be composed. So you can have like a restarting behavior, an adapter, or all kinds of different behaviors that you can compose, which actors didn't compose that well in that sense. You could make one actor talk to another and then compose them this way, but you couldn't just, on the type level, combine them like that. And the sender is gone, which is surprising to many people, but you'll see it's very good because it allows for less bugs, and it's actually a performance win as well. So here's an untyped actor. You get a message who to greet, you set a variable, okay, the greeting is this, and then once you get the next message, you print the greeting. This is just to show that we have some variable, we have some mutable state, right? So in the mutable style of the new typed API, you would extend the mutable behavior, and here's how you would construct the actor. So actor mutable, it will handle commands, and here we give this greeter. And the greeter, as you can see, it can only receive commands here, and you do basically the same thing. So not much change, right? And basically the purpose of this API was to not change too much, because we want people to migrate very easily to this new API. However, let's look at the immutable API, which we think is more pure and more functional in a way. In the immutable API, you don't extend the class, you just use functions. So the actor immutable, handling commands, actor context, and the message that it can receive. Message would be obviously a subtype of command. So this has a good side effect that the compiler in Scala can look at the type of command, and if you had 3 commands and not 2 like we have here, and you only matched 2, the compiler would warn you that, hey, you forgot to handle one of these types, maybe you need to add this case. And what we do with the state is we return a new one. So greeter behavior returns basically self, right? It's the same method we're in, but it returns itself with this new state here, right? So this is how we do state in the immutable actor API. If you want to reply to someone, as I said, sender is gone, you would include a reply to actorref, and that's good because now it's typed, right? So whoever sent you the message can tell you what type of message you can send them back. So, so Java doesn't have pattern matching, but actually it's been brought up as a considered feature, so it's nice to see Java kind of confirming all of the Scala design choices. Nice to see. So in Java, you can do an immutable actor, and we provide a builder API. So it's close enough to Scala. You have to do a bit more curly braces, but very, very close. Please have a look at it. It's out in the open, and there's a lot of blogs and articles that we wrote, so you can have a look and kind of get a feel. And it's in a phase where we want a lot of feedback from the community, so please let us know. Okay, 5 more minutes. And last 2 topics. So Alpakka. So it's a pun on Apache Camel, basically. So what we want to do with Alpakka is basically have a community of streams connectors, and we contributed a lot, and the community contributed even more. And it's about implementing reactive streams interfaces for all kinds of databases, queues, and other systems. So here's a list of stuff. And this basically means anything that is on the list here, it's a one-liner to connect Akka to it. You basically want to go to S3, you run with S3 sync, done. And you can put stuff into S3. And it will respect the back pressure and the synchronous nature of reactive streams. So explained in 2 seconds, if something fits by type, it will automatically fit because everybody is implementing the same underlying protocols. So it's not only about types, but also about behavior. And we strongly believe that investing in the ecosystem rather than we implement everything ourselves is a bit more powerful. So if you have a favorite, I don't know, database or queue that isn't in Alpakka, please contribute it. The entire purpose of it is to be very inclusive. And the last thing, so Artery, which is our new remoting subsystem. We've polished it a lot recently, and it's not fully stable yet. So if you want to give that one a try, please do. And it's a bit more than, yeah, we changed the transport to Aaron. So the classic, how we call it, Akka remoting was on TCP. TCP doesn't really fit well with messaging that we do. So we switched to Aaron recently by Martin Thompson, which is UDP based. And we did it basically allocation free in a steady state. So what I mean by that is, so this is how you can use it. It is already included in the latest versions of Akka. You just flip a switch and you suddenly are using this one, and you get like a 10x performance improvement. Pretty good. With exactly the same semantics and 0 code changes. So in a steady state, we basically don't allocate anywhere on the sending side. So yeah, you serialize your data, but the byte buffers are pooled, so you don't allocate here. None of the infrastructure is allocating because Akka Streams can be fused and allocated just once. And yeah, the receiving side of a Artery connection has to allocate only in one place, which is where it deserializes the buffer into your data type, right? Can't get around that. We do a lot of compression as well. So this is a typical actor message, and you can see it being dominated by, so the message is hello, right? So that's the message. And all of this is just metadata, where it has to be sent to, where it's coming from, etc., etc. So what we do nowadays is, well, in Artery, is we apply compression, and the compression is also automatic and transparent, and it negotiates which actor is most important to compress and compresses those first. So we can save a lot of data, as you can see, up to like 70% for small messages. For bigger messages, it's not that important. Okay. The last thing I want feedback from you is we're doing some multi-data center work. So we're looking at use cases. If you have a use case about multiple countries or multiple data centers, talk to me. we're looking at what we can provide there. And the extras, which I'm running out of time for, is basically the commercial things we're offering. So just to say, this is what earns my bread, kind of, because everything is before is open source and freely available. This is what pays our salaries, which is distributed tracing and metrics. So you can have all kinds of metrics just out of the box for Akka, including which are the most chatty actors. This is the actors that would be that actor compression would be applied to. Some other tools, tracing. To enable tracing, you only need to do exactly these things, and you have distributed tracing across multiple nodes and across HTTP calls as well, very shortly. IntelliJ is working on Akka support, so they have a booth here. You can talk and ask them for what kind of Akka feature you want. There's .NET and JS ports, and a vibrant community. So this is all I had. This is the mini book if you want to have a look. It's bit.ly why reactive. As I said, it's a good intro. It talks about basically how to think about reactive architectures. Not as much about the programming side, but about the architectural side. So, illustrations by Lep-Pung Cheng and myself. So the terrible ones are by me, obviously, not the other way around. And if anyone has any questions, I'm happy to take maybe one or two. Thank you. So hands up if anyone wants to ask a question right now, otherwise I'm available as well during the day. Calling once, calling twice. One question over there on the left. Mauricio, if you...
Why should I choose Akka Streams instead of any other implementation of Reactive Streams for Scala like Monix or something like that? Okay. Why Akka Streams?
Compared to Monix. So Monix, one second. Yeah, okay. I don't want to search the slide yet. I don't have a comparison with Monix in the slides, but Monix is closer to what RX is doing. They are very focused on maybe let's put it like high throughput, but not as much evolvability or connections to other stuff. So what we have in Akka Streams, for example, is the entire infrastructure is geared for monitoring. Because we learned the hard way, and maybe I should have put this in this talk, that just doing a really fast thing is very simple. Okay, it's not the problem in distributed and concurrent computing. We had that, we had zero introspectability. You would have your fast system and then it breaks and you have no idea what actually broke. So the kind of difference with Akka Streams is that the entire infrastructure is very introspectable. And we'll be working on right now actually on if a thing fails, why did it fail? What was the context? What was the incoming request from Akka HTTP? In which context this stream has failed, and correlations like that. And the important thing is, if we do that, and when we do that, we do it for all kinds of stages, not only for the built-in ones, which is the problem Monix and RX Java and RX Scala, etc. have, because all of the stages they have are one-off. There's no single point to instrument. You have to instrument all of the, okay, I have to instrument map separately, I have to instrument filter separately. Everything has to be a one-off there. So in our infrastructure, we instrument the entire infrastructure, and even if you build custom stuff in Akka Streams, it will be monitored, it will have all these things. But otherwise, if you just want to use Monix and connect it to Akka Streams because you want to use something from Alpakka, that will just work because everybody implemented RX, so our S. Sorry. I hope that answers. Last question. Calling once. Calling twice. Last chance. Okay, thank you very much then.